by anything. But I've thrown in a couple of fun extra sentences for people who know math and have a strong math background. If I say a sentence and you know what none of the words mean, just ignore it, leave it be, it's fine, you don't need to understand it, it's not for you. Alright, so the goal of this talk is to kind of give an introduction to harmonic analysis, and it's okay if you don't know what that is. But we're going to start somewhere a little more elementary, and that is Fourier analysis. So just show of hands, who's heard of a Fourier series before? Damn, that's a lot of you. Nicely done. So for those of you who haven't heard before, a Fourier series is essentially writing a function as an infinite sum of sines and cosines. And the reason that we do this is there's a certain partial differential equation that shows up all over physics called the heat equation. And we can solve it when some initial function is a sine wave or a sum of sine waves. Now, most mathematicians saw that and went, okay, we're boned. Like, most functions are not sums of sine waves. Fourier looked at that and went, which functions are sums of sine waves? So the driving question for Fourier was, if we have a function f from the interval 0 to pi, and for now I'm going to work with the real numbers, when is it the case that f is equal to the sum from negative infinity to infinity of alpha n sine nx? When does this happen? The answer is basically always. It is shocking how often this happens. Every continuous function, check. Functions with a finite number of discontinuities, check. Functions with infinitely many discontinuities, usually check. And the condition that Fourier came up with was that if the integral from 0 to 2 pi of the absolute value of f squared exists and is less than infinity, then we have this. Then we have that f is an infinite sum of sines and cosines. And what's more, we can explicitly compute these coefficients, and it's not that hard to do. Now, a function obeying this property, we will say that f is in L squared of 0 to pi, comma r. That's just a bit of notation for us. Okay. Now, I took PMAF 450 with Blake Medill, and I saw this, and I thought this was a cool theorem, and I asked him, how can I learn more about this? And he said that harmonic analysis generalizes these ideas. It generalizes the notion of a Fourier series. My question was, how the fuck do you do that? I mean, okay, we have a f here. It can be discontinuous, it can be unbounded, it can be basically anything, and we can still write it as a sum of sine and cosine waves. And what's more, most of the functions that do not obey this property provably don't have a Fourier series. So it kind of seems like this question is completely answered, right? Like, we have solved this problem. So how do you generalize it? And that's a hard question. But it turns out that if you reframe this fundamental question of Fourier series in terms of an area of algebra called representation theory, this very naturally generalizes itself to many, many more settings. So just as a bit of housekeeping, first of all, I'm not going to think about functions going to R. I'm going to erase this and add a C. And I'm going to write f equals sum negative infinity to infinity of cos nx plus I sine nx. Because this turns out to actually be the more useful problem. And for those of you who know anything about complex numbers, this whole central term can be grouped as a complex, oh, I should have had coefficients. But this central term can be grouped as e to the in. And I'm just going to erase this second r here and just put a closing bracket to signify that we're going with complex numbers. Okay. And the other bit of housekeeping I'm going to do is we have our functions going from 0 to pi, from this half-open interval of complex numbers. But there's actually a more natural way to think of this as the functions having a domain not of an interval, but of the circle, S1. For those of you who have not seen this notation before, S1 is the complex unit circle. It's everything, distance 1 from the origin of the complex plane. And the reason that this reframing makes sense is that these e to the I n x's are actually just all of the points on the complex unit circle, and so it might be natural to think of that as our domain. And the reason we can think of that as our domain is if we have a function, like, let's say this is 0, this is 2 pi, and the graph looks something like this, we can sort of wrap this function around the circle. So we can think of this point as being the horizontal on the circle, and this 2 pi being what you get when you go all the way around. So we can think of these 0 to 2 pi's as representing an angle on the circle. And this way we naturally get a function that comes from the circle and goes to the complex numbers. And the advantage that this mathematically has for us is this thing is what's known as a group. Now, if you haven't heard of a group before, there's this sort of technical definition. A group is a set with a binary operation that obeys 3 obvious properties. So you have that A dot B dot C equals A dot B dot C, associativity. There exists some identity element such that G dot E equals E dot G equals G for all G, and for all G, there's an inverse element. So there exists an H, so that GH equals HG equals the identity. The circle is a group with the operation being add the angles, or multiply them as complex numbers. There are lots and lots of examples of groups, but what the group axioms are really trying to capture is the idea of symmetry. And what I mean by this is if I have some object, let's say this wonderful juice box here, and I'm doing actions to it that leave it unchanged, let's say rotations along these 2 axes, that set of actions would form a group. And the reason is if I'm physically doing something to an object, I can always undo it. That gets us our third axiom of the inversion. You can always just do nothing to it. Observe. Wow, I'm so cool. And finally, if you do A, then B, then C, that's the same as doing A, then B, then like that's words. It's obvious that those 2 are the same thing. But for those of you who are currently taking an introductory group theory class or have taken one, let's say PMath 347 or 336, you might go, hey, that's not what group theory is at all. Group theory is pushing symbols on a piece of paper. And okay, maybe intro courses are kind of taught like that. But when you move to an area of math called representation theory, this perspective becomes almost immutable, of groups being symmetries. So before we define our big juicy object, we're just going to need one last little definition. If I have 2 groups, G and H, a function phi from G to H is said to be a homomorphism, which I'm going to write just as hom because I don't like writing, if phi of GH equals phi of G, phi of H. Ooh, this is a bad choice of letter, but these G and H are both elements of G. The reason we care about this kind of function is if we just let functions go between groups willy-nilly, that would kind of forget the group structure. In the sense of a group is defined by 2 things. It's defined by the underlying set, yes, but it's also defined by the multiplication. And so if we're working in a group theoretic context, we don't want our functions to just be between the sets, because that doesn't care about the multiplication. We want our functions to preserve what makes a group, and what makes a group is the multiplication. And so we do the multiplication either before or after, it doesn't matter, but in this way it preserves the multiplicative structure of the group, which is what defines the group. So now, a representation of a group G is a map. So a rep is a map phi from the group to what I'm going to denote as GL of V. For those of you who haven't seen this notation before, GL of V is the general linear group of a vector space, which is a set of invertible linear transformations on that vector space. Now, this thinking of a homomorphism, especially if you've never seen homomorphisms before, can be kind of intimidating. So the way I would like to think of this, and this is a correct perspective, is to think of elements of your group as transforming the vector space. So you've been given this group from up high, and its elements are doing something to space. They're rotating, scaling, shearing, shifting, whatever. And so you have a picture in your mind of what the group is doing. Now, this has a couple of very clear upsides. First of all, linear algebra is really easy. Like, not classes. I struggled so much in Math 245 and 146. But linear algebra is basically solved from the perspective of research-level mathematicians. If you give a research mathematician a linear algebra problem, they'll be able to say, oh yeah, this paper, whatever, solves it. Just because we have powerful theorems like Jordan canonical form, we have cyclic decompositions, we have the existence of eigenvalues when our base field is complex. There's so much theory in linear algebra that we can solve most of the problems incredibly easily. So this gives us a linear algebraic way to understand our group, while also giving us a geometric and visual intuition about what it's doing. Now, any one of these representations individually actually, unfortunately, doesn't tell you that much about the group. But the collection of all the representations together tells you a ton, which is really exciting. With the slight caveat being there are infinitely many. But luckily, there is a compact way to express what all of the representations are. See, when I have a representation, if its image has a non-trivial invariant subspace. So if every element of the group, let's say, fixes the same vector, I can pick a basis where the whole image will be block triangular, with the blocks corresponding to the spaces that are fixed. And then I can break up this homomorphism as a direct sum of those blocks. And if you didn't understand that, that's totally fine. The idea is there exist representations which are called irreducible ones. And every representation can be built out of these irreducible representations. Further, if our group is finite, we are guaranteed there are only finitely many of these irreducible representations, which is fantastic, because they're not that hard to find. And so once you find all of them, you know everything about the representation theory of the group. And once you know everything about the representation theory of the group, you're able to recover a ton of algebraic properties about it. Now, given a representation, there's something that turns out to be really useful called a character. So I'm going to go back over here. Sorry, Fourier, your life's work is being erased. A character, chi, is a function from our group G, the complex numbers, defined by chi of G equals the trace of phi of G. So this chi depends on the representation we have over there. You can define the character of a representation. Actually, to make that notationally clearer, I might do chi subscript phi. But I really tried to come up with an explanation for why this is useful that's intuitive. And honestly, all I can say is if someone asked you to sit down and find the irreducible representations of a group, you would need to think about the eigenvalues of the elements of the group at some point. There's an excellent book called Fulton and Harris that's sort of an intro to representation theory, and it has a little section that just kind of ad hoc does the representations of the symmetric group on 3 elements, and it's a gross argument. But most of the way that it works is by figuring out things about eigenvalues. Now, the trace, as you'll remember, is the sum of the diagonal entries of the matrix. But that's equivalently the sum of the eigenvalues, because you can always pick a basis where your diagonal has your eigenvalues. And so this chi is somehow capturing enough about the eigenvalues that the characters on a group, if I just tell you the characters, it completely determines all of the representations, which in turn recovers a ton of information about our group. Okay, let's just think about a couple of basic facts that we can say about these characters and these representations. First of all, any representation on a finite group will have all of the eigenvalues be roots of unity. And the reason for that is, okay, our group is finite, which means that by the pigeonhole principle, g to the n is going to be the identity for some n. And if we think of this g not as an element of a group, but as a linear transformation, the eigenvalues of g to the n are the nth powers of the eigenvalues of g. And on the right-hand side, we just have the identity. And so all of the eigenvalues of this are 1, which means the nth powers of the eigenvalues of this are 1, so all of the eigenvalues are roots of unity. What we can further say is that if this V is one-dimensional, then phi and chi are actually the same thing. And that's just because if you're working on a one-dimensional space, then the only linear transformations on a one-dimensional space are the scalars. And the trace of the scalar is the scalar itself. Last sort of big point, I guess I will write these down. The big one that I want to write down, irreducible representations of a commutative group. For those of you who haven't heard the word commutative before, it just means multiplication order doesn't matter. A times B is the same as B times A. The irreducible representations of a commutative group are one-dimensional. And the reason for this is that commuting matrices always share an eigenvector. And that's an invariant subspace, right? The eigenvector is the simplest invariant subspace of a linear transformation. So unless this V is one-dimensional, if your G was abelian, then you have a one-dimensional shared invariant subspace, and so you can break down the representation further. The reason I'm going through this trouble is we're now going to be talking about representations of infinite groups. And if you just let the representations be homomorphisms from the group to some general linear group, you end up with way, way, way too many, to the point that you can't say anything useful anymore. But if we let, so for an infinite group G, for G infinite, a rep pi is a continuous map. For those of you objecting to me talking about continuous maps on a group, I'm assuming that we have some kind of topology. In the case of our circle is a subset of the complex numbers. So we can just talk about continuity as we would in the complex numbers. If you're not comfortable with abstract topology, keep that specific example in mind. We have continuity on the circle the same way we have continuity on the complex numbers. So this is a continuous function, pi colon G, again the general linear group of a vector space, but such that pi of G is unitary for all G. Now, in practice, this unitary for us, the only property of it we care about is that all of the eigenvalues are going to land on the complex unit circle. Now, what this means is that if we have some kind of infinite abelian group, like let's say our circle group, the characters of irreducible representations, chi on S1, okay, well, they have to land on the unit circle, and they have to be continuous. So we're looking, and they have to be group homomorphisms, because you'll remember all of the irreducible representations are one-dimensional, and so the character equals the representation, and so since the representation was a homomorphism, the character was as well. So the characters on this circle group are continuous maps from the unit circle to the unit circle, which also are homomorphisms. And we can actually find all of these explicitly, and it's not too much work. And the reason it's not too much work is that if I have, remember that trick we did before where we said, okay, functions on the interval 0 to 2 pi are the same as functions in the unit circle? We can go the other way around. Given a function from the unit circle to the unit circle, there's a unique, so given f from S1 to S1, there exists an f hat from 0 to pi to S1, such that hat f composed with, composition's going to go on the other side, e to the I x composed with hat f is equal to f. And what this is really saying is if we have a function on the unit circle, we can unwrap it and stick it on the real line and get a function whose domain is the real line. Okay, so now we can ask, what are the group homomorphisms? And actually, I guess we can make this a 2π periodic function on all of R. So our original quest of finding all of the homomorphisms from S1 to S1 can kind of be restated in terms of finding homomorphisms from the real numbers to S1. And we can actually do the exact same trick on the other side. We can kind of, instead of working with S1 here, we can unwrap that to the interval 0 to 2π, because we can take everything in the codomain, like every point on the unit circle, and associate it with its angle. Because every point has a unique angle, and so what we're really looking for are the homomorphisms just from R to R. And then we can compose these with e to the ix and get all of the homomorphisms from the unit circle to the unit circle. Now, these are not hard to find at all, because we have the continuity assumption. See, the integer 1 needs to get sent to some other integer. So, or I should actually say, because, it gets sent to some integer multiple of 2π. And the reason for that is that when we unwrapped our function and put it on all of R, it ended up 2π periodic. And what that means is that, what that implies is that we kind of have this, if we look at the graph of the function, it'll do something like this. And so wherever 1 gets sent, that determines where all of the other integers get sent. And then using continuity and the continuity of multiplication, that'll tell us where all the rational numbers get sent, because we can sort of deduce what 1 over x had to get sent to, and that'll finally tell us where all of the real numbers get sent. And we know that 0 had to be sent to some integer multiple of 2π. And so every integer must also be sent to the integer multiple of 2π, and then that tells us where all the rational numbers go, and that tells us where everything goes. And so really, our only choices for homomorphisms from R to R are scalars, where x gets sent to Rx. And that means that our where specifically R here is going to be an integer. And these are the only things that will both work as the group homomorphism and be continuous and keep the periodicity we want. Which means that all of these characters on the circle group S1 are in the form e to the inx, where, e to the in, where n is some integer. So we have the characters on the circle group being these e to the inx's. And what we said was that every function in f in L squared of g is equal, or in this case, I guess we should put S1 here. Our square integrable functions on the circle are equal to an infinite sum of these characters. Equals sum, negative infinity to infinity, alpha n e to the I n x. So we've now turned this analytic fact into a purely algebraic, well, almost purely algebraic fact. We've said that we can decompose any of the square integrable functions in terms of the characters. And that is a statement which generalizes much more easily. Because we've asked this about the circle group, but what happens when we put another group there? What happens if we put a group that doesn't commute there? What happens if we put a group there that isn't compact, because the circle group is compact? And the answer is that a slight variant of this always holds. This is the so-called Peter-Weyl theorem. So if we let G be compact, but not necessarily abelian, and we let its irreducible representations be given by the spaces e pi, there's sort of a natural way to embed these irreducible representations in the square integrable functions on G. And that's done using what are called matrix coefficients. So in our 1-by-1 case, our characters were naturally functions that were L squared, because our characters took in elements of the group and spat out complex numbers. But the representations in general will spit out matrices. However, you can just look at the entries of those matrices, and then you get functions for the complex numbers, because each entry of the matrix is going to be a complex number. Now, you don't do exactly that. You take these things called matrix coefficients, which you get by taking essentially inner products of the matrix entries, but it's the same idea. You look at what's in the matrix, and you build different continuous functions out of that. And the Peter-Weyl theorem says that L squared G has an orthonormal decomposition in terms of the irreducible pies that looks like this. What this is essentially, this d pi is the dimension of this space e pi, and this space e pi is the space of the matrix coefficients. So you essentially get all of the irreducible representations with a number of copies equal to their dimension. And basically, the intuitive reason you get a number of copies equal to the dimension is that you have d sub pi linearly independent things in there. The matrix has d pi squared entries. So you need d pi copies of this to capture what every entry of the matrix is doing. And this statement gives us the original Fourier series, but it also gives us substantially more for many more groups. And in particular, what it does is it allows us to translate algebraic questions into analytic questions. Now, if you have a question about the representations of some topological group, you can instead look at this Hilbert space. Hilbert space means inner product space. There's a nice inner product here. You can look at this Hilbert space and kind of look at how it decomposes, and then you get clear insight into what the representations of the group must have looked like. And you can use functional analysis to, for example, talk about these operators. Are they compact? Are they bounded? What can we say about them in general? Conversely, if you have analytic questions about this Hilbert space, or any Hilbert space isomorphic to it, you can use the algebra that you know about this group to answer questions about it. And that is the real power of harmonic analysis. It allows us to turn these analytic questions into algebraic questions and the other way around. And the people working in harmonic analysis are also often working in another field: number theory, pure algebra, possibly functional analysis, because the point is that they're using harmonic analysis to understand more about their field of choice by referencing another field. So I guess the last thing I'll say is that there are many, many more generalizations we do in harmonic analysis. So this, the characters I talked about, the group of characters on a set is going to be, on a group G, is denoted hat G. And for those of you who have seen Fourier stuff before, you might notice a suspicious similarity to the notation for a Fourier transform. And that is not a coincidence. The dual, the character group of the circle group was the integers. And the Fourier transform takes in a function and then spits out a function that takes in integers. There's this beautiful theorem called Pontryagin duality that tells you the character group of the character group of a group is the group itself. And this, if you've, again, seen any Fourier analysis, this captures the fact that the Fourier transform is, in some sense, its own inverse. There's the fact that the Hilberts, these spaces, are always isomorphic, well, under some very weak assumptions. Which captures that the Fourier transform actually gives us the coefficients of the Fourier series. There are so many more things you can say. And the point is that by reframing the basic Fourier theoretic questions about sines and cosines, in terms of this representation theory, it naturally lends itself to a wide class of generalizations that are interesting in mathematics, physics, and so many other fields. Thank you everyone for coming.
Does anybody have any questions for Nick before we start the next talk?
I have a quick question.
Yeah, Captain?
So I guess in the one side you were talking about the general version of the groups, where you said it was a sum of the irreducible characteristics, or those that have no analog of irreducibility over the have e to the I compose like e to the
Guys, please be quiet.
e to the I2x and e to the I3x. I get e to the I6x.
E to the I5x. You multiply them and then you add, but yes.
Yeah, right. And so that's violating the.
No, okay. So no, it's not about being able to write the thing as a sum of other representations. Irreducibility is specifically about non-trivial invariant subspaces, and all of those are one-dimensional, and so they don't have an invariant subspace that's non-trivial because the only subspaces are trivial. That's why I presented the correct definition, and just what you should think about is that every representation can be built up out of irreducibles. But the converse, being able to write a representation as a product of two other representations, that tells you nothing about reducibility. It's a one-way street. Any other questions? Yeah? So, a representation is by definition a map to a group of matrices, and harmonic analysis is by definition the study of the representations of groups. Oh, right. So keep in mind here, the functions themselves were never involved with matrices. The functions lived in the Hilbert space, and all we did was decompose the Hilbert space in terms of the representations. The representations are the things that involve the matrices. The functions living in the Hilbert space don't have to have any connection. So all you need is for your function to live in the appropriate Hilbert space for some means, and you'll be able to do the harmonic analysis.